Hi, my name is Prashant Joshi. Today we are going to take a look at data serialization using Avro and sequence file. In this topic, we are going to cover what is serialization and what is its connection with big data, available serialization formats, what is sequence file format, what is Avro format, summary and observations. Most of the data is currently stored either in the XML or JSON file format, which are not fit for Hadoop file systems. The reason for this being the lack of synchronization markers for these files, thus making those files difficult to split and determine the start of the next records. The big data files, or the files that are used in big data, should have some specific characteristics. The important one being that these files should have the ability to be split into multiple files so that they can be processed parallelly, and they should be in compact size and have schema evaluation capabilities. So what are the important characteristics which should be considered while selecting a serialization format? Transparent compression, splittability, support for the Hadoop ecosystem, schema evaluation, language support, and code generation. Available serialization options are sequence file, protocol buffer, thrift, Avro, and Paraquet. Let's see what is a sequence file format. These formats offer the highest level of integration with Hadoop and its ecosystem. They are splittable binary format that stores data in key value pair. There are three types of sequence file format based on how the compression is applied: uncompressed, record compressed, and block compressed. So what are we going to do here? So our problem statement is partition the data into multiple files based on the country name. Here we are going to use the patent data that has been supplied, and we'll use this in this example. So let's see how to write a file structure for sequence file format. And in the meantime, let's go through the coding part. To create a sequence file format, first we need to identify the structure of the data that you want to represent. We are not going to take all the columns that are present in the patent file that we have, but I have here captured first 8 columns: patent, year, date, country, post date, assignee, and assign code. So the first part that we should do is make sure whatever Java Pojo class we are writing, it should implement the writable comparable class so that it can be used as key or value. We should override the read fields method. We should override the write method. We should override the comparable method. And I have provided one utility method called readLine, which will help to convert each record in a line into the patent writable Pojo class. Next, we need to write a writer class. In this writer class, I have written a method called writePatentFile, which is responsible for converting our file into sequence file format. The key points here is the options that we need to specify for a sequence file. First one is the path where this needs to be written. What is the key class? Here we are using the text as a key class, and the value class we are using patent writable as a value class. And what is the compression strategy? Then the system goes on to read each line of our input file, convert it into a patent writable object, and append that object to the file writer object. Now I've written one utility method to clean up and copy. Now let's take a look at the structure of our MapReduce class. The partition file, let's say, it extends the configured class and implements the tool class. So we have a mapper class called sequence file mapper, which will read the file and which will read the file and it will write to the multiple outputs which will actually divide that file based on the country name. So here we are passing text as the key and the print writable as its value. There is no reducer class in this program. Now let's see how the run method is structured. The first method is called the cleanup and the copy file. This method is responsible for cleaning the existing file in the HDFS directory and then copy the input file from the local directory to the HDFS directory. And then we define the name of the class jar where this partition file, file is stored. Then what is the mapper class? What is the output key? What is the output value class? What is the input format class? What is the output format class? And the compression strategy for the generated files. And then I am just reading a country name for that file. Oh yeah, so this is how the program will look like once run. Here you are seeing that our patent data has been converted into the sequence file format and the job has been processed, and we are seeing the list of the file, and we have read one file with name CS. Now let's see the output. Let's see some of the key takeaways from our project. First is the sequence file has got inherent support from MapReduce class and MapReduce ecosystem. It lacks schema evaluation, which means that changing the schema of that class is a very cumbersome process, and it doesn't support versioning. It's a very good choice if the files are processed within HDFS and is processed by MapReduce or its big or Hive ecosystem. So some of the observations that I have noted is at times, the mapper class was not getting loaded because Hadoop was not loading the jar file in which it is there. So I have to copy the jar file in the HDF system and provide a libjar option to run this class. What is Avro? Let's take a detailed look at how Avro format looks like. This is also a compact binary format, the option to compress the file. It supports schema generation, but it's optional, and it allows dynamic discovery and data interaction. The schema is stored as a part of a header, thus making the serialization process simple and has less restrictions on maintaining the schema outside the data file. There are two notions used for writing the data. First is the generic data, with which no specific schema is applied, and the second one is the specific data, which allows you to work with the Avro primitives. Now we can work with Avro file format. Here we are going to convert the text file into Avro key value pair format and demonstrate how it can be used in the MapReduce job. Avro works in two forms. First, schema generation, and the other one without schema generation. In this example, we will use schema generation to manipulate our data. We'll use the patent file. And the first step to convert this text file into Avro file is to define a schema. The specs for the schema is defined in the URL provided. We'll use the avrotools.jar to convert the patent schema into an implemented Pojo class, and we'll import it into our IDE. I've used Eclipse as an IDE here. This is how the patent looks like. We have a name, type, namespace, and different fields that we want to capture. Next, what we need to do is to write a utility method which will convert our schema into the actual representation of Avro files. Let's deep dive into the code now. This is how the Pojo looks like, and go into the utility method which I have written to convert the input file into the appropriate Avro file format. All these steps are performed into the HDFS file system. First, we need to define the schema for the key value pair that we want to represent. So we want to represent the key with an integer value, and our value will be the patent object. Next, we define a generic data writer object, and then we will set some of the properties as to how the file needs to be compressed, when it will be flushed, and what is the sync interval. I have a utility method called populate data, which will read each line and convert that record into the patent info object, and in the Avro key value class or instance, it will populate the key and its value. Finally, this record will be written or appended to the generic writer. After that, we close all the streams. This is a utility method to read the Avro file, the generic record. Now let's see how it is implemented in the MapReduce. We need to import two important files, two important jar files. One is the avro.jar and the Avro mapred hadoop2.jar. So these two jar files are required so that our class would compile. Next, we write a partitioner class. In this partitioner class, we will extend it with a mapper class, which will take Avro key and Avro value as the input parameters, and the same will be used as an output parameter. We'll override the map class and define it accordingly. Same thing we'll do with the reducer class. Now let's see how the jobs are configured. We have first create a job class, and then we'll define what is the input format. Then we define what is the mapper class. This is the most important piece. We'll define an Avro job, and we'll define the schema that is required for this job, for the Avro job, and we'll pass the job instance into this method. Similarly, we define the Avro value schema. What is the map output key, map output value schema, and what is the output file format, which is Avro key value output file format. We'll define the Avro output schema, we'll define the output value schema, and then we'll define the compression strategy which is used for our example. Now let's run this program. The command is running, the Hadoop jar is running. It will take some time because it takes time to convert it into the Avro file format. It's more than 230 MB, I believe. Now it has converted. I have just printed the first 20 characters of this file and to display and show how the key value structure of Avro file format looks like. Now that you have seen how Avro file format works, let's see what are the key takeaways. First, Avro file formats can be created with schema generation or without schema generation. We have seen an example of schema generation here. The fields are ordered using their ordinal position in the schema. You can customize this ordering by defining the order property for a given field by either it can be ascending, descending, or you can ignore the ordering altogether. Summary. Both sequence and Avro file formats are row based, meaning all the fields are written in a row, followed first row followed by the second row and so on. Most big data job needs reading at column level. Entire row is read even if the data is not needed for one or two columns, thus requiring more I/O operations. Use of columnar storage can help solve this problem, keeping the advantage of compression schemes intact. Thank you.